Good morning, everybody. Thank you very much for coming to this early talk. My name is Thanh. My colleague Siddharth was supposed to give this talk with me, but unfortunately, he cannot come today. We are both doctoral students from Aalto University in Finland, and our research focuses on analysis and design of network security, network protocols, as well as application security. And in this talk, I will talk about security of inter-process communication, or IPC. In this talk, I will show that application developers usually think that IPC is inherently secure and don't pay much attention in securing it. And I will show that this is a huge misconception, as the data transfer over IPC should be protected in the same way as over the internet. So the structure of the talk is as follows. I first discuss the threat model that we call man-the-machine or MITMA, and then I will warm up with some basic about IPC and its attack vectors, which make many software vulnerable to the MITMA threat model. I will then go through some case studies of real-world software applications that are vulnerable to the MITMA attack model. And finally, I will sum up with some mitigation mechanism. All right, so let us get started. First, let us understand the man-in-the-machine threat model. So we see software with client-server architecture everywhere. Let's take the browser and the web server, for example. In the traditional network threat model, the user device and the server are typically trusted, but the network is hostile. The attacker can do various types of attacks, such as man-in-the-middle, to steal the data that exchange over the internet. And since we are aware of such attacks, we use crypto solutions such as PKI, such as TLS and the Web PKI to protect the communication. However, in reality, not all the communication goes over the network. Certain part of the communications that happen within the computer, for example, software often comprises of the front end that provides a GUI and the back end that manages the data. They are separate processes, and they use a mechanism called inter-process communications, or IPCs, to exchange data. These communications stay within the computer and never leave outside. However, there can be adjusted component inside the computer, and protecting the user information exchanged over IPC is equally important as over the network. So for these reasons, in this work, we try to understand the security of the communication inside the computer with focus on IPC security. And this is a MITMA threat model. We consider the threat from malicious processes inside the computer. However, we are not interested in malware because we think that if the computer is infected with malware, everything will be compromised. So instead, we're interested in legitimate processes run by other users, and these processes are supposed to be on the computer. In our threat model, the attacker can be any unprivileged user that tries to steal sensitive information from other users on the same computer. The example of potential MITMA attackers are colleagues or family members, and the target system here is any multi-user computer. Computers that can be accessed by multiple users are very common. Think of enterprises and university, for example. Their centralized access control is used to allow any employee or student to log in to any computer. And in such environment, everyone has their own credentials, have their own personal computer, but this computer can be accessed by any domain users with their own credentials. And we also found that the attacker can be any guest user too. Many operating systems, such as Ubuntu, they enable guest access by default. So the attacker could be anyone, not just insiders. So how does the MITMA attacker to attack other users on the same computer? The attack method here is to run malicious process from the attacker's login sessions. An example attack scenario is as follows. the attacker signs in to the victim's computer with his own credentials and runs the evil process. He then uses fast user switching on Windows to leave the login session in the background. So this way, the evil process will continue running in the background and try to exploit the IPC of the victim when the victim is using the computer. On macOS and Linux, it's even easier because a process can be kept running in the background without leaving the login session in the background. And things could even be worse if there is remote access such as SSH or Windows Remote Desktop enabled on the computer. With these, the attacker could run the evil process from remotely. So before talking about how the mid-malware attacker can exploit IPC use in security critical applications, let us now dig deeper into IPC and its attack vector. There are many types of IPCs, and not all of them are vulnerable to the mid-malware attack model. The common feature of vulnerable IPCs is that the server process binds to a name or an identifier and waits for connection from client processes. And in this work, we focus on 3 IPC methods, which are network socket, name pipe, and USB human interface device. Strictly speaking, USB is not IPC. However, USB communication also happens inside the computer and shares a common feature of the as other vulnerable IPC method. So it leaves the mid-malware attacker to exploit it. There are also IPC methods that are secure against our attacker model, such as socket pairs or unnamed pipe. The difference is that both of the communication endpoints of this communication channel are created by the same process at the same time. So this way, an untrusted process cannot get into the middle and exploit the channel. And now let's take a look at each of the vulnerable methods one by one. Let's begin with network socket. So even though network socket is usually used over the network in computer network, it can also be used as IPC. And in fact, it's one of the most widely used IPC. Here, the server listens on the loopback interface on a specific port number and waits for client connections. As long as the port number is higher than 1024, any process, regardless of its owner, can listen on the port. And with network socket, only a single process can listen to a port at a time, but multiple clients can connect to a server. And there's no built-in access control to restrict who can be the endpoint of network socket communications. So this leaves local attackers like mid-malware to exploit it. And one of the obvious things that the mid-malware attacker can do is client impersonation. Attacker can find the port number from documentations, source code, or simply by running netstat and connect to the server as a client. So there could be cases where the local server accepts only one connection. So if the attacker comes later, its request will be discarded by the server. In such cases, the attacker just needs to connect to the server before the legitimate client does. So the question here, if client impersonation can be done, then is it also possible to do server impersonation? Well, yes. So the attacker just had to start the local server before the benign server does. And there's nothing that can stop this attack. The client would not notice that it would not notice this is not the right server, and simply connect to the port and start exchange information. So at this point, some of you might have noticed that legitimate and malicious servers cannot bind to the same port at the same time. So can the mid-malware attacker do man-in-the-middle attack on the network socket communications? Well, it's still possible. So here, attacker first needs to perform server impersonation. That is, it runs a local server on the legitimate server ports, and on this primary port, it can receive connection from the client. Many software while running local server, they fail over to a secondary port when the primary port is already taken. This port agility makes sense from the software point of view because this software, they don't use standard port number. So some other legitimate process on the computer might already have taken the port. So switching to another port does make sense here. But this, however, gives an advantage to the attacker because after doing the server impersonation, the mid-bar attacker just needs to connect to the beeline server on the secondary port, and then to perform the client to perform the client impersonation attack, and then we have the man as middle. Then of course there are cases where such port agility is not implemented. In such scenario, the attacker can switch his role between impersonating the server and client. He can time it well and exchange information between the B9 client and the B9 server, similar to that of man's middle. However, this will be slower. So now that we know network sockets on localhost are vulnerable to midmar, what about name pipe? So name pipes are available on most operating systems. However, they differ in the implementation. Here we are interested only in Windows name pipe. Windows name pipe have a similar client server architecture like network socket, but instead of localhost, the name pipe instance are placed in special path where everyone can access, including guest users. And instead of the port number, each name pipe has a specific name. With network socket, there's always one server and multiple clients can connect to it. But here with name pipe, there can be multiple instances of a name pipe, and all of these instances share the same name. There is exactly one pipe server and one pipe client that can be connected to each instance. And when the pipe server process runs, it waits for the pipe clients to connect to it. And once client process join a pipe instance, the pipe server process or even another process can create a new instance and wait for a new client. There's a major difference between name pipe and network socket. That is, name pipe have built-in access control. So name pipe are basically Windows object, so they have a discretionary access control list associated with them. And there are two cases here. When the pipe doesn't exist, anyone, any user, including guests, can create a new pipe and set the access control list of all the future pipe instances. However, if the pipe does exist, only those users with 5 create pipe instance permission can create a new one, and they cannot change the access control list of the pipe anymore. So, thus having access control stops name pipe from being vulnerable to midmar attacks? Unfortunately, no. So, similar to that of network socket, the midmar attacker can perform client impersonation by simply connect to any open pipe instance. And even though they are subjected to access control, we will learn from the next slide that this access control doesn't matter at all. And just like port hijacking or taking over the port before the legitimate server does in network socket, the midmar attacker can perform server impersonation simply by hijacking the name of the pipe. He can hijack the name of the pipe just by creating the first instance of the pipe and set the access control of the pipe so that anyone can create or connect to any new instances. And this way, the B9 pipe server just create a second instance without knowing that there's already an existing one. There's some flag which can be used to detect whether the pipe instance is the first one or not. However, we found that many software developers miss such options, leaving the name pipe communication vulnerable to the midmar attacks. Similarly, the benign client process can connect to an open Pi instance without noticing that the owner is not the legitimate owner, but the attacker. The man-in-the-middle attack is pretty straightforward with name pipe. The attacker just needs to perform client and server impersonation at the same time and forward messages between the Pi instances. So now that we know about socket and name pipe, let's now talk about the last IPC that we consider, the USB HID. So what is common to network socket, name pipe, and USB HID communications? So even though USB is strictly not an IPC method, USB HIDs still bind to an identifier and wait for connection as well. So it leaves them vulnerable to our threat model. We are interested in these devices because hardware security tokens such as YubiKey that we use for second factor is also USB HID. The Linux and the Mac OS implementation is different from that of Windows. In Linux and Mac OS, the USB HID devices can only be accessed from only the current interactive user login sessions. But however, in Windows, no such access control mechanism exists. So more than one user at a time can access the USB HID, even the one in the background. So this means that the security of this USB HID depends on the application layer security mechanism implemented in the software or in the hardware device themselves. So now I will show how we can exploit the vulnerable IPC method in password manager and security tokens. Our primary case study is standalone password managers. So they're different from cloud password manager like LastPass in that they provide a native desktop app that allows users to manage their password. These password managers are often integrated into web browser with browser extensions. And these browser extensions assist users in storing password and entering the password into login pages. And the browser extension and the app communicate the password over IPC. And in this work, we analyze various password managers to see how they protect the channel. The first case study I would like to talk about is RoboForm. The RoboForm app runs a HTTP server on port 54512 and waits for client connections. The RoboForm browser extension connects as a client to the server in order to query the password from the app. The problem with RoboForm is that there's no authentication in the on this IPC channel, and the app will respond to any client without verifying that it's actually the legitimate RoboForm browser extension. So it's quite easy for the mid-mark attacker to exploit RoboForm. The attacker here is any unprivileged user that's running malicious process in the background. So he can easily perform client impersonation just by connecting as a client to the app and query the whole password database from the app. The second case study is 1Password, another popular password manager. This is more interesting because 1Password tries to give some security on the IPC channel, but it's not good enough to defend against the mid-mark attacker. Here, the app runs a WebSocket server on port 6263 and waits for connection from the browser extension. When the server got the connections, it verifies the client very carefully. It checks the browser extension ID in the HTTP header. It checks the code signing signature of the client process to make sure that it is a known browser. And most importantly, the server checks whether the server and the client process are owned by the same user. So with these checks, we couldn't perform client impersonation on 1Password. However, the client here does not verify the server. It actually cannot, because the browser extension is sandboxed by the browser and it has access to very limited API. So this allows the mid-mark attacker to perform server impersonation. Even though the client and server They run an ad hoc protocol in the first communications to exchange an encryption key, but the design of the protocol is not secure enough to prevent the server impersonation attack. So let us take a look at the protocol. This is how the protocol looks like. And the client here is the browser extension, and the server is the desktop app. There are several problems with this protocol. So we can see here, first, all the material of the final key, you see the HBAR key and the nonces, they are sent out in the messages. And second, we can see on step 4 and 5 that the users has to the code that user has to compare is just a random string. It has nothing to do with the protocol values. And also, on step 5, the user only confirm on the app side. It means that a malicious server can just skip this confirmation. So this insecure protocol, together with the fact that there's no server authentication, no server verifications, allows the mid-mal attacker to perform server impersonation. So now I will walk us through how to perform server impersonation on 1Password. So attacker just need to run a WebSocket server on port 6063 before the desktop app does. And when the app tries to run the server and see the port has already been taken, it just fails silently without informing the user. When the attacker server got connection from the browser extension, it does the key derivation protocol, so as I described before, but skips user confirmations. So here, unlike RoboForm, the mid-mal attacker cannot access the password database because it's performing server impersonation. But we found that the attacker can send a command called collect documents to the browser extension to collect all of the data that the victim enters on web forms, and this data includes login credentials. So we have seen two password managers that use network socket as IPC channel. Many other password managers use native messaging instead. This is a standard browser's built-in method that's designed to provide a more secure alternative to network socket for communicating between browser extension and native code. So how native messaging works with password manager? So password manager first register with the browser an executable called native messaging host and allow only its browser extension to access this native messaging host. And when the browser extension wants to communicate with the native messaging host, the browser will run the native messaging host in a child process and communicate with it using standard input and output. So this way, the mid-mal attacker cannot get into the middle and intercept the connection. So the question here, is native messaging a perfect solution for password manager? Well, unfortunately, no, it isn't. The reason is that the native messaging host and the password manager app are still two separate processes, and they need to exchange data over IPC. So the only difference here is that the native messaging host is not sandboxed by the browser, so it has more options on how to communicate with the password manager app. So let's take a look at an example here. Password Boss is an example of password manager that uses native messaging host. Native messaging. On Windows, its native messaging host uses namepipe to communicate with the native app. And when the app starts, it creates a namepipe and waits for connection from the native messaging host. So native messaging host simply connects to the namepipe as a client and forward messages between the browser extension and the app. However, the app and the native messaging host here, they don't authenticate each other, and all messages are sent in plain text. So because of these issues, we were able to perform man in the middle on Password Boss, and we could do it not only from an authenticated user, but also from guest users. So let me first show how the man in the middle attack could be done from an authenticated user. As I mentioned, when the app starts, it creates a name pipe and waits for connection from the native messaging host. So first, the attacker just needs to connect as a client to the app's pipe instance. And then the attacker creates another instance of the pipe and waits for connection from the native messaging host. And when the native messaging host tries to communicate with the app, it will connect to the attacker instance because it is the only open instance of the name pipe. And after that, the attacker simply forwards messages between the two pipe instances, and we have managed the middle attack. It's a little bit more tricky to perform the attack by a guest user because, as I mentioned before, the access control list of the pipe allow only access from authenticated user. So it means that a process running from a guest user cannot connect as a client or create a new instance of the pipe. So the solution here is pipe name hijacking. The guest user could create the first instance of the pipe and set full access to all users. So this way, when the app creates its instance, it doesn't even notice that another user had created the first instance of the pipe, and access control of the pipe is not as expected. And the rest of the attack is exactly the same as the attack by an authenticated user. So last case study I would like to talk about is the FIDO U2F security key. So FIDO U2F is standard for the second factor authentications, and it's supported by many popular services such as Facebook, Google, and GitHub. And most security keys implement this standard, including YubiKey and the new Google's Titan security keys. You can see on the right that this is a simplified protocol of how the U2F security protocol works. So first, the user must register the device with the online service that it wants to enable second factor. So basically here, the device generates a public key pair, and the service links the public key to the user. After that, when the user wants to log in to the service will send a challenge to the browser, and it expects to see a response containing the device signature on the challenge. To get the response, the browser will repeatedly send a challenge to the device until it receives the response. So the device here doesn't automatically sign any request it receives. It needs to be activated by touching a button on the device, and it only responds to the first request after the touch. So now we show how the mid-mal attacker could exploit the U2F security key. And since the security keys is supposed to prevent malicious login even when the user password has been compromised, we assume here that the attacker has already obtained the victim password and are trying to correct the second factor. So attacker will exploit the fact that on Windows, any user, even the one running in the background, can access USB HID devices at any time. So the attack is as follows. The attacker first runs a malicious browser process in his login sessions and signs into the service using the password that he has obtained. The malicious browser will receive a challenge from the service. After that, the attacker will keep sending the challenge from the service to the device at a higher rate than a legitimate browser would do. So this way, it will increase the chance of getting the challenge side. This is pretty easy because Chrome, for example, sends a challenge to the device every 300 milliseconds. And when the victim signs into any service using the same security key, the victim will touch the button on the device, and there is high probability that the attacker's request will be signed because it is being sent to the device at a higher rate. The user might notice that the first button has no effect because it is used by the attacker. But such minor glitches are typically ignored. So we tested the attack on popular services, including Facebook and GitHub, and got 100% success rate. So we have seen how we exploit the driver form, 1Password, password boss, and FIDO U2F keys. But those are not all the applications that we found vulnerable to mid-mal attacker. And this is a list of apps that we analyzed and their vulnerabilities. Password managers and other login credentials are our focus here. We also found vulnerability in other apps that follow client-server architecture. MySQL, for example, on Windows, if client and server are on the same computer, and the client can, so in that case, the client can connect to the server using namepipe. We were able to perform man in the middle on this channel, and we could obtain all the queries and query results on this channel. So how can the mid-mal attack can be mitigated? Since attacks are performed by leaving a malicious process running in the background, the most straightforward solutions would be to limit the number of users that have access to a computer. So ideally, each computer should be personal to a single computer, to a single user. Remote access should also be disabled or limited to only one user. The mid-mal attack can also be easily detected. The application developers just need to compare the owner of the server and the client process. But it's a little bit more difficult for JavaScript client running in the web browser because such client they don't have access to the OS API and they cannot perform the owner check. So in that case, cryptographic solutions can be used, such as TLS and the PKI. So in conclusion, the main takeaway message from this talk is that the software developer should be aware that IPC is not inherently secure. There has been a common belief that nothing we can do to defend against local attacker. It may be true if the user device is infected with malware. However, as we have seen, there are many other potential attackers, and any user, regardless of its privilege, can attack the IPC of other user on the same computer. And unlike malware, so the application developer can totally defend against this attacker. So this is the end of my talk. Thank you.